Hey everyone, welcome back to day 3 of Design Verification Professional Training Program. So today we are going to learn about how the test bench will be written in System Verilog. Means let's understand class based test bench, what is the importance of class here, and how we will be randomizing the data, why we need to randomize, where actually that will be helpful, and how we will be putting the constraints while doing the randomization. All these will be understood with a simple example. You will get a complete verification code using class, and that will be useful in your understanding of design verification concepts. Let's get it. Yesterday we have seen DUT instantiation inside a test bench, and also we have seen how we will be randomizingly generating the stimulus, and we have seen a simple checker, right? This will be giving pass and fail percentage, pass and fail values out of 100 test cases. In our case, let's say 50, 50 are failed and passing means these are the numbers we have seen yesterday in a simple test bench. Likewise, we will be having a standard scoreboard, and that will give you the exact result that DUT performance is correct or not. DUT functionality of the DUT is correct or not. That is scoreboard. So this kind of test bench we will be seeing again in today's session. Okay. Then coverage and test strategy, test case development will be understood as we go further in this training. Okay. So then we have seen verification of an adder already yesterday. This is the design code we have seen, and we started with this. Here we will be providing only three possible cases. Similarly, as I told you, to just to provide some inputs to validate a calculator, right? You will be providing 4 plus 2, and if it is 6, it is correct. Then you will be checking 1 plus 2. If it is 3, then it is correct. You may check multiplication as well. 4 into 2, if it is 8, it is correct. Like that, if we can check manually, we can provide hardly some 10 cases, right? Here we have provided 3 such cases. Through this, we can't say this design is working fine, right? In verification, we need more test cases. We need, okay, to exactly tell the design is working fine. So what we did in the next stage, we added randomization. Correct, we used these two constructs. We use $u random range. This $u random, okay, can be used on any variable. Let's say is equal to $u random. This will generate some random value for a. Let's say the a value is 42, something like this. But a is restricted to 3 down to 0 here. It can generate a maximum value as 15, right? But if you just say a is equal to $u random by declaring a as an integer int a, it will generate a 32-bit value. Okay, remember this. This $u random will be a random number generator. It will generate a 32-bit value. So we can use $random u random for any variable like this. Okay, but here we improvised the u random and used $u random range. U random range. So we can use $u random directly. It will give you the random number. If you use $u random range, and if you provide the range of values you need, let's say 0 to 10, then it will give you only the values between 0 to 10 randomly. So this is a Verilog construct. Similarly, if you use $u random, let's say in my some test case, I need to provide more than 10 to 15. I need to check for the maximum value of B it can attain. Let's say it's 10 to 15. Then we can provide like this. In the previous case, what happened? We are restricting ourselves to A is equal to 2, A is equal to 3, A is equal to 4, B is equal to 1, A is equal to 7, and B is equal to 0. These are very simple cases like this, right? Now, system itself is generating you the random value for AB. Okay, if you sit and write AB values manually, You need to start with A is equal to 0, B is equal to 0 combination first. Then you need to check for A is equal to 1 and B is equal to 0 combination. Then you need to provide A is equal to 2 and B is equal to 0. Continuously you will be provide A is equal to 15 and B is equal to 0. This is one set of value. Then again you will start with A0, B1, right? Similarly it will go till A is equal to 15 and B is equal to 15, right? This is very tedious process. We can't do like this. It is a 4-bit variable so that we can provide 0 to 15, 0 to 15 combinations. But if it is more than that, we can't do manually. That's why these randomizations are required. Okay. And also we can run them for how many number of times we need. Here we are putting these under repeat block. Remember this also. We can use repeat and we can provide how many times we need. Repeat 50, begin, and I need random value for AB. So A is A dollar random, and let's say B dollar random, and end. This will generate random 50 combination of values A and B. Okay, this is one way of generating the random value. In this case also, because of this issue, yesterday we have seen this already, right? This is the issue. For adding 3 down to 0 A, 3 down to 0 B, we need to have 4 down to 0 sum, correct? But designer has designed with 3 down to 0. This is a bug. This is the issue in the design. It may work for small values. Okay, if you take 4 plus 2 as 6, it may work. Why? Because 6 will be represented as 0 1 1 0. Okay, 3 down to 0 supports. If you add 4 plus 6, it may support. Okay, it is 10. If you go more than 15 for some, it will not support. It will not give you the actual result. The 1 bit will be truncated and only 4 bits will be present inside your sum, right? So that's why we need to have 4 down to 0 here. This is the mistake we need to identify by providing a bigger value for AB, correct? Here we have a question. Let's understand that. Sir, those range parameters should be written in decimal. Yes, you need to provide it in integers. Okay, random range. This random range work on integers actually. It will generate some integer value. It will just generate the integer values that we are taking into A. Okay, that's it. It is not dependent on the type of A what you have declared here. So we need to provide integers here. So that is a good question. So now come checker into the test bench. What we did here, what the improvement we made to this test bench is we added pass fail as two variables, and we know that we need the expected value as a 5-bit value. So we added 4 down to 0 here for expected, right? And we also added expected is equal to A plus B as internal calculation, and if sum is equal to expected, we are incrementing pass, otherwise fail. Okay, if you don't know this syntax and all, don't worry, I will explain you from tomorrow in detail each and every line. Now let's understand in a abstract level. So here we are indicating fail and pass numbers. You can see 34 pass and 16 cases it's failed because of this 3 down to 0. If you just change this to 4 down to 0, so that you will get correct result. Again, here is a question from Jyoti. Sir, what is the difference between $random and $urandom? Yeah, I will cover it now. See, $random will generate, okay, it will generate signed values, signed numbers. $urandom will generate unsigned numbers. It will generate unsigned. Unsigned mean all are positive numbers. We are going to consider the number generated by $urandom are unsigned. All are positive numbers. If you use $random in place of that, it give you the same integer number It may have negative also. Means in MSB, if it is 1, then it will be a negative number. Only when we need some negative numbers also as part of the input, you need to go for $random. Otherwise, you can use $u random. I will show you that. I have an example here. Okay. So now the question is why this randomization is so important in verification. Is it so important to use randomization? Yes. Already we have seen some cases. Verification is not just about checking expected cases. Okay. Manual test writing is very slow. We can't cover all the possible values and it is limited. Random stimulus removes human bias. This is very important. Okay. Simply if you provide 4 plus 2, that is a biased value. Only it will check for 4 plus 2, 4 and 2. Then functional coverage can be obtained by providing more random values to cover most of the part of the design. Functional coverage will be good if you use randomization. Random test stress the design. It will also provide 15-15 as AB, a maximum value. If the designer has not handled the maximum value capacity in your design, you will find that error. So these are some corner cases. You may not try out this maximum value calculation when you do it manually. So these are some of the advantages why we need randomization. So Jyoti, you asked what is $random and what is $u random. See here, $random is a random number generator. Okay, old Verilog random number generator. What it generates 32-bit signed number. The signed number range is this to this. Okay, minus 2147 483 6482 plus 2147 483 647 means if you represent any number with 32 bit by considering a signed bit, MSB bit as sign, then this is what the range is. Okay, you can see here simply I have used $random here. This is $random I used, and I am printing that inside a string by taking a decimal equivalent of that here. See here. So this is this is the output of this through this display. This is a simple Verilog code module, Verilog randomization initial, repeat 4 times, means we are running this line for 4 times. We are getting 4 results. You can see 1, 2, 3, 4. These 4 are the first statement results. This is a positive number we got. This is negative number. This is negative number. This is negative number. The first one is positive number. Means through $random you may get different numbers which are positive or negative. We have an interesting thing here. See here we have $random and we are providing a value. Okay, remember this. This is very very important. There is a concept of seed in randomization, in verification. Let's say there is a concept of seed. Okay, random seed. What does this seed mean? We need to understand. See, suppose if you want to grow a mango tree, what seed we need to put here? What seed we need to use? Mango seed, correct? Mango, sorry. We need to use mango seed, correct? Similarly, if you want to grow a jackfruit tree, what kind of seed we need to get? Jackfruit, correct? So the seed is that depending on the seed, you will get a similar kind of result here. You will get only jackfruit in this plant, in this tree. Similarly, if you put a mango and if you grow a mango tree through this seed, you will get only mangoes out of this, correct? Similarly, if you want to generate some standard values, not standard values, let's say some fixed values, a fixed kind of values, then inside the system to generate these values, there is a seed associated with that. For a random number generator, if you provide something like 5, it will generate 5, it will not 5, it will generate same number of values repeatedly. How many times it generated? 4 times. Why? Because here we are just using that 4 times. If you use 40 here, repeat 40 times, it will generate the same value 40 times. Okay? So this particular number, okay, inside your system is having a seed called 5. 5 is a seed. If you provide 5, always the system will give this number. Okay. So this is one concept which will be very much helpful in verification. Why? Because let's say we are running one test case for 10 times. Okay. And all the 10 times we are randomly generating some data. Always we will be randomizing the data. Out of these 10 test cases, 9 times it will pass. You will get pass result. In one test case, it will fail. Okay, in one test case, it may fail. Why it will fail? In this one test case, because of this kind of some particular values generated, and it will be having a particular seed, that seed is generating some kind of values. For this set of values, it is failing. You need to identify, oh, why my design is failing for these kind of values only. 90% of the time it is passing. Then this is your corner case. Some corner case of your design got hit. It is not so well developed, designed. So you need this seed value. For this random set of values, let's say some seed number is 256. Some seed number is 1025. Something like this. Some value is there for some standard random values. Okay. So you can get the same values again while randomizing, means you need to provide the same seed. That's it. Why we need seed now? I think you guys have understood. 90% of your design is working fine. It is failing only in one test case. You want to know, you want to debug the design, means let's say again we will try with the same values. If you want to get same values and you are also randomizing, if you want to have a control on this randomization, means you need to know what is the seed for this set of values I provided. For that particular value it is failing. You need to regenerate your test case. You will be testing your design again with the same set of values, means you need to provide that seed something like this to the randomizer. Suppose again I will go back to your calculator checking. This is your calculator. You will check 1 plus 2, it is working fine, 3. You will provide 2 plus 3, it is working fine, 5. If you provide 10 plus 11, it will working fine, 21. Suppose if you check for 9 plus 9, other than 18, it is providing 17. Only this value, it is providing error. In that case, if you're randomly simply clicking some value and getting the result, you need to remember for 9 plus 9 only it is 17, right? So if it is randomly generated, there is a seed associated with that. If you know the seed, then it is easy to recreate that error whenever you need. Okay, that's why seed is very, very important. Then we have $u random that we have seen already. $u random will generate. See here, all those are positive values. All are positive, 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 positive. And also we can provide range in $u random. This range is not available in random case. $random will not support range. $u random will support range. Okay. And in $u random, U mean unsigned. Here, $random means signed. Remember these things. These are very important for interview. Then let's understand a system Verilog thing for randomization. Are we keep on doing this for every signals what we have? Just suppose where it is like this. Here we have only A, B. Okay. So we use $u random for them to generate the random value. Suppose if you have 50 input signals in your DUT, this DUT has 50 input signals. This is your processor. Will you write 50 signals and randomize like this? Is it possible? No, it's very difficult. 50 times we need to provide, and we need to provide the range. That is tedious process again, even if you randomize them. So we have a random number generator in system Verilog called randomize. Randomize. This randomize is a function. Okay. So if you just say randomize A, it similarly work as $random and it will generate you the random number, but it will not be used for a particular variable. It will not be used for a particular variable. It is again becomes $random, right? Correct? Are you guys understanding what I mean to say? Have you guys understanding how randomization work? Please respond. Understanding the purpose of randomization at least? Yes. I'm expecting response from everyone. Don't worry about all the constructs what we are using here. Don't worry about what is initial. Don't worry about what is reg, why we need to use. Don't worry about why we need to keep this under if. Don't worry about when $display executes. What is this double quote here? Why we need to put bracket here. Don't worry about the syntax. I will cover you all these from tomorrow. That. Okay. So the next way of randomizing is through randomize function in system Verilog. Here, this is a very simple example shown here just to get to know how this randomize works. We can use randomize function for a variable, randomize of A, it will randomize this A. But this is not the exact use case of randomize. We need to understand class now. Why? Because system Verilog is, remember, SV is Verilog plus oops. Object, here it is, object oriented programming, that is oops. Your Verilog doesn't have any oops features. It doesn't know where oops. Okay. System Verilog support oops. Through Verilog only you can do whatever I have explained so far. You can randomize the things by using $random, $urandom. But system Verilog supports this randomize function and it supports class-based test bench. Okay. So now we need to understand what exactly the difference we have between Verilog and system Verilog, correct? We need to understand the difference first, right? Then only we will come to know, oh, these many changes are there in system Verilog, that's why we need to go for this, right? So let me directly take you to that first. Let's come back to this randomization. Okay. See here. These are all, okay. These are all the differences we have between Verilog and system Verilog. Actually, this page is not sufficient. It is actually going down. Okay, there are some more lines here. So if you want, if you can take a screenshot. Okay. See, these are the features we have. The purpose of using Verilog is for RTL design. System Verilog is for RTL design and also for verification. This enables complete verification environments. Then the second one is data types. We have only reg and wire here. You know how many data types in system Verilog? We have logic, we have bit, we have byte, we have int, enum, struct, everything. Third one is object-oriented programming. It will not support. This supports. Fourth one is classes. So here class mean an object-oriented programming, inheritance mean a part of object-oriented programming, polymorphism, encapsulation, randomization, not randomization till encapsulation. These are part of object-oriented programming concepts, right? Then randomization, that we have seen randomize function. We can write constraints. Constraint means for the randomizer, you can set a rule that the value of A should be in the range of 1 to 10. You can put that constraint. Or A should be only even numbers. Like that you can put a constraint. It should be only odd numbers. You can put a constraint. It should be only 2 power numbers. You can put a constraint. So we can have more advantage of randomization through constraints. We can generate a better randomized value through constraints. Why these things are required means, suppose in some designs, it is taking only even numbers, it is taking only odd numbers. Or let's say if you are verifying some block, every alternative block we need to verify. Okay, that might be one of the scenario. In such case, you need to target only even locations. In that case, through randomization, if you generate a random value, it will generate 12, it will generate 25, it will generate 42. We can't cover, right? We need to go with each and every even numbers. Then you can put that in a constraint. Your randomizer consider that and generate in that fashion. That is constraints. Then we have assertions, functional coverage. These are the uh, these are the features we will be using for verification, property checking, and verification completeness through functional coverage. We use interface, mod port, mailbox, semaphore, event handling, packages, enums, structures. See, even in arrays, we have many types in system Verilog. Dynamic array, associative array, queue. These are the three main arrays we have. And string type, process, test bench capability. Okay, here it is basic, here it is advanced. These are the differences we have in Verilog to system Verilog. Because of these advantages, we need to go for system Verilog for verification. Okay. Now let's go back to our randomizer function. And we need to understand class now, what exactly class is. Okay. So directly I will take you to some example. Yeah, see here. Let's directly jump to the usage of class. Here, this part of code is a class. This is your module. Okay, this is your module. This is your class. Okay, what exactly class consists of here in our test bench means we will be having the data members here. Data members directly can be referred to variables, what we have declared. Variables inside a module, we will be declaring AB, right? In your adder case, those AB can be written inside a class now. Now, if you put it under a class, and you can observe inside a module, this packet class is called here. You can see packet, correct? See here, we have packet, and we are giving an name of that packet inside my test bench is P. Now we will be accessing these address and data through P. If you use P dot address, then it's referred to the class member address. You can assign some value like this: P dot address, P dot data. If you want to access a class property, okay, this is a class property. This is a class property. Then you are supposed to use the class handle. Inside TB, how that class is accessed? Through packet P. P is the name we are providing here. Packet is called as P. And remember, before using these class variables or class data members, we need to call function new. This is the standard way to construct an object. To construct an class object inside your module, construct an object of packet. You need to use this function new. This will be called as standard constructor. This will construct the object. Okay. Now after calling the new function through that handle, then we can access the data members present inside a class. We can have a function inside a class. We can have a task inside a class that can be accessed through this P. We can't directly access packet.randomize, packet.display. We can't do that. Okay. This is a simple example of class. It is just like we have declared previously, let's say module TB, and inside the module we declared bit. Bit is a system Verilog data type. Remember, bit A, let's say bit B, and we have bit 3 down to 0 something like that, correct? Now we are doing this, all these inside a class. We are keeping them separately. And we are utilizing the name of the class here, and we are naming that as P inside my module, and I am calling a new function to construct the object. What happens when we call a new function? There is a memory allocated for these variables: address, data, These are the two locations indicating the address and data where actually it sits. Okay. Now we can use the repeat statement to generate the values. How we will be generating here? We are not using address and data to generate the random values for them. Directly we are randomizing the object itself. See here, this line, check this line, what it is? P dot randomize. What we are doing here? What exactly P dot randomize do? This P internally has, when we call the new function through P, it allocated some memory for address and data, correct? And P dot address means this. P dot address is this pointer. P dot data is this. It is pointing to this location. Whenever you randomize, the new values will go and sit here. Okay. If you just call P dot address, this will come out. If you call P dot data, this will come out. So in a single line, even if you have 50 declarations here, 100 declarations here as data members, you can randomize all these at once. Okay. And we are calling 10 times. You can see here, this is the first randomized call. You are getting address as some value, data as some value. Second time, address is some value, data is some value. Third time, fourth time. How many times we got this result? 10 times. Correct? Why we are getting 10 times means we are repeated 10 times. Here, repeat 10. So both the data members getting randomized here? Yes. Are we accessing address and data for randomization? No. How we are randomizing? Through the object name, through the handle of that particular class. This is the advantage of having randomized function. In your DUT, let's say if you have 50 input signals, these 50 input signals will be declared here once inside a class, let's say packet. And if you just say p dot randomize, you will see all 50 values generated. No need to write 50 times, correct? So this is the advantage of having class-based test bench. Now there is another advantage here, another topic here to discuss. We have declared bit address, bit data. Along with that, we have a declaration called rand. We need to indicate the data members of class as rand so that whenever we call randomize function, they will be the part of randomization. Otherwise, if you don't use rand here for data, you are using only for address, then only address will get randomized, data becomes 0, 0, 0 every time. Means you are skipping the randomization for data. You are only randomizing this address. Okay, you can do that. In some cases, let's say, in your case, suppose if you have some control signal, let's say start. Start is one signal. This should be always one, then only your DUT will function. In that case, do we need to randomize this start? No. Always it should be one. Then no need to declare that as rand. But that will be the part of P. After randomization, in this line here, you can write P dot start can be equal to 1. Then all the time this will be 1. Okay. And we have an alternative for rand as well. We have rand C. The difference between rand and rand C is that just observe the results what we obtained here. Just look at data. Okay. Please reply me. How many values we generated for data? 10 values. Why? Because this is 10. And what are all the values we can have for data? We can have from 0 to 7. Correct? This is 3 bit, 2 down to 0. All 0 to 7 values are generated. If we generated 10 times, can you guys check this data value and tell me? All 0 to 7 are covered. Have we covered? Have we got all 0 to 7? Okay, let me check. 0 is there. 1 is there. Where is 2? 2 is not generated. Where is 3? 3 is not generated. Where is 4? 4 is not generated. There are 2 5s. There is 1 6. There is 1 7. There are 4 7s. There is no 8. Okay, 8 will not generate, correct? So even if we exercise this for 10 times, we are not covering all possible cases. Our intention is to cover all possible cases, correct? That is why we are going for randomization. Manually, we can't write all those possible cases, correct? But here we are missing out some combinations of input. Even if we exercise this for 10 times, if we run it for 20 times, it may cover, but we don't know. So other than going for RAND, you can go for RAND C. This RAND C will cover everything. See, I have an example for that here. Using RAND C, the same example code, address data. Other than declaring them as RAND, we are using RAND C here. Okay, here you can see RAND C, RAND C. Now look at data. Can we count in the same way? Can we check all those possible cases 0 to 7? Do we have 0? Yes. Do we have 1? Yes. Do we have 2? Yes. Do we have 3? Yes. 4? Yes. 5? Yes. 6? Yes. 7? Yes. At the first 8 iterations only, we got all 8 values. Correct? Can you observe the difference now? Please replay. Can you observe the difference between RAND and RAND C? Now we are getting all possible values for data. Yes. This is the advantage of having RAND C. Whenever you need all possible cases to be covered at least once before any other value repeats, you can use RAND C. Okay. Now check the address. Check the values for address, what it generated for in first 10 iterations. Is there any value repeated? Any value for address repeated? No, right? What is the maximum value address can take? What is the minimum value and maximum value it can take? It is a 4-bit variable. It can take 0 to 15, right? 0 to 15 it can take. We have 0, we have 1, we have 2, we have 3, we have 4. There is no 5, it is not generated 5, it is not generated 6, it is not generated 7, 8 is there, 9 is there, 10 is there, 11 is not generated, 12 is not generated, 13 is not generated, 14, 15. All are unique values, correct? Means at least 16 iterations are required to get all values, right? This is how RAND C works. Until and unless we cover all the possible cases at least once, the value will not repeat. In such cases, you can use RAND C. Then, is that sufficient? Randomization is sufficient here with uh, these features? No. We need some more constraints. We need some more rules we need to add with the randomization. See here in this example, we have that. Look at this line, p dot randomize. With this condition, this is your condition. You are putting a condition to the randomizer that let p dot data generate inside 1 to 5. You should get the data only between 1 to 5. I need this. Then you can put a constraint. This line will be called as inline constraint. Okay. Here we are restricting the randomizer that, hey, don't generate data more than 5 and less than 1. Keep it in between 1 to 5. Now check the data. Are we getting values in between 1 to 5? Data, are we getting in between 1 to 5? To have only these values in randomization. I don't want more than this. This will be called as constraint. If you write that along with the function call, randomize call, then it is called as inline constraint. Okay. These things are used predominantly in industry. Every day when they write some test case, when they randomize, the same kind of lines we write. Okay. Remember, these are industry use cases. Okay. Then let's go back to our module TB what we have seen. So for now, for these 3 days, this code is like a gold. You can keep this as a reference. We have the same module here, design code. test bench start from here. This is the test bench starting point. We have a class now. In the class, we have declared AB. Okay, we have AB here. In the design, we are verifying through this test bench. Other than declaring inside a module AB, we are declaring it here as rand. Okay. Don't worry about this constraint, I will explain. Don't worry about this display, I will explain. Just consider these two lines. Inside a class, we have AB and end class. Now module TB, the same adder instantiation here. We have instantiated in the same way. Now you can observe this. We have used this class directly here. Are we using the same class? Are we used in the previous example? Here class packet is used as packet P and we are calling new function. Correct? In the same manner here we are using this transaction, class transaction as T. Okay? Under initial begin you can see T is equal to new. This is object creation, means new is a constructor. Means we are calling the constructor to construct object T. This will allocate some memory. Then we are displaying that system Verilog class based test is executing. We are repeating for 50 times. Now we are not supposed to use $random here. We need to use randomize. Correct? See here T dot randomize we are calling. Can you see T dot randomize here? This is the randomizer we are using now. Okay. On this transaction object, it will be having AB. Once you call this function, it will generate some values for AB. How many times we are calling? 50 times. Okay. Then we got these randomized values through T dot A, T dot B. We need to pass that to the test bench variable AB. Then this will go to DUTA, DUTB. Correct? This we understood yesterday. What is the instantiation? That's why we are taking this T dot A and putting into A. T dot B and we are putting into A. This is where we are driving to DUT. Otherwise, your T dot A, T dot B will be present inside the test bench only. When it will reach, when it will reach your DUT, when you are pointing that to the instantiated variable. Here you have used A. Here you have used B. This A you have used here. This is the B which we have used here. Correct? And what is this A? This is your input A. This is your input B of your DUT signal. This is your DUT signal. Right? Now this A is coming from here. This B is coming from here. It will reach AB. It will generate sum by executing this line. And we are taking that sum from here. Right? Now we can have an expected value inside and we can take this carry and sum and we can along with the expected we can compare it here. If it is pass, we are increasing a pass. Initially it will be 0. Then we will be increasing fail. If it is failed, else part, then we will be displaying fail. These things are same as before. But through this example, we understood this class can have the data members which are required to be randomized, which are the input signals to be randomized, input A, input B to be randomized. So we have used those two in a class called transaction. Then we have used $randomize. Don't worry about it, why we have used inside if this randomization failed, we need to get a warning or we need to get a error. That's why we used inside if. This can be used as a condition. If randomize, if you use like this, if it fails, we will come to know if you put a condition or a display here. Okay, don't worry about that. Let's understand later. Now, this code will give you pass and fail result. Okay. Now remember, in this class, we have class called transaction. Okay. Here we are randomizing. Let us call this as data generator. Okay. Now this is your DUT. Let us call it as DUT. Here you are driving to the DUT through AB. Let us call this part is driver. Okay. You are getting back sum and carry. Okay. This sum and carry what you have here, you are getting back to the test bench through this instantiation. Let us call this part is we are monitoring the outputs monitor. Okay, we are checking here with equals operator, right? Let us call this as a checker, or let's call it as a scoreboard. It is giving you the score of your test, right? Scoreboard. So now we need to have a generator, we need to have a driver, we need to have a monitor, we need to have a scoreboard. Suppose if we write them inside a separate class, means what I do in next, I will randomize it in a class called generator. I will drive those signals in a class called driver. I will monitor my output in a class called monitor. I will generate a score in a class called scoreboard. This we are doing inside a simple module now. Why? Because this DUT is very simple. We can write everything here one after the other. But if your DUT become complex, as we separated out the data here and at a time we are generating through randomize, we can also separate out the data generation. We can also separate out the driver. We can also separate out the monitor and scoreboard. Okay. That is your actual system Verilog test bench is. See here. Can you guys relate now? Can you replay? Can you replay yes if you can relate things? Now you can see driver, you can see monitor, you can see scoreboard, you can see generator. Okay, right? This is how we need to understand. Directly we can't understand what is generator, what is driver, what is monitor, what is scoreboard. If you even if I give you the system Verilog test bench, you need to understand where data generates, where actually the driver part will come, where the monitor part will come, where actually the scoreboard part will come. Okay, this is the actual test bench in system Verilog. We have module TB, we have test, we have environment, we have generator, driver, scoreboard, monitor. These things we have seen. Generator means we will be having data generation. Driver means we will be pointing to the input signals of the DUT. Monitor means we will be collecting the outputs here. In scoreboard we are saying pass or fail, right? Only this much we have in a system Verilog test bench. Other than that, to control these we have environment. To control the environment we have test. To control the test or to put all together we have test bench top. In between we have an interface to connect the DUT. This is a standard test bench how it look like in a system Verilog. Okay. So let's understand this later. Now if I bring you to the system Verilog test bench, after this just introductory session of today's session, you will not understand much code. Again, we need to go in a surface level. I don't want to bring you there. You need to learn it perfectly, correct? So let's understand the Verilog test bench fully. Let's understand the Verilog constructs fully. Then we will be understanding this test bench in system Verilog. That is what the plan is. That's why uh, in our program we have minimum 3 months course. In that minimum 3 months, what we are planning is in the first month we will be going through Verilog and digital. In the second month, we will be going through system Verilog. In the third month, we will be going through UVM. Okay, that is how we need to plan. If you directly go to system Verilog also, if you directly go to UVM also, you will not understand. You need to know at least Verilog test bench constructs fully so that you can relate easily. See in this 3 months what we are covering here. Yeah, this is the brochure for both 3 months and 6 months program. At first you can see 3 months program and then later you can see 6 months program. This is our 3 months structure. In 3 months we are covering, in the first month we are covering digital design and RTL foundation. Even if you are an absolute beginner, even if you don't know anything in Verilog, if you don't know digital design also, but you know some basics of electronics, you should know gates and all, you can start with this. Okay, you will know how to write a Verilog code for any design. Then in the end of first month itself, we start system Verilog. Here you need to understand from data types and constructs. Then there are procedural blocks and advanced concepts of system Verilog we need to understand. Then directly we need to jump to classes. Then test bench components, driver, monitor, sequence, and scoreboard, all those. Then verification of RAM. We need to do a project here. We need to verify RAM. This can also be done here. In Verilog also we can verify the RAM functionality. Simulation and debug practices is there, right? Here we will be covering that. You will understand how we will be writing a verification code for simple RAM. Then that RAM will be connected to an APB. APB is a protocol. You need to understand the protocol. So protocol based verification project will be covered here. Before that we will be covering RAM project also. Then there are some coding practices and there are some assignments and exercises we need to perform it here. Then in the third month we will be jumping on to UVM. Here we will be understanding what is the test bench architecture, why we need UVM, applied verification concepts. Then the same APB project what we covered in system Verilog will be ported to UVM here. This is the actual standard way to understand things. Also, we will be covering APB Verilog here. Then you will understand APB system Verilog here. Then you will understand APB UVM here. That give you a confidence that the same code written in Verilog will be converted into system Verilog like this, will be converted into UVM like this. Then introduction to AHB protocol. This is some advanced high performance protocol. Then deep sessions, interview focused on discussion and project preparation, and then interviews and placements. Even for 3 months, we'll be supporting you with placements. Okay. If you are a quick learner, you can learn more things other than these as well. I will suggest you. Then if you want advanced program also, you need to you need these things for project placements. Actually they will ask AXI protocol, they will ask AHP protocol implementation. These are some good projects, you can put it in resume. You can put this APB, and you can put, if you put 3-4 projects in your resume, it will be easily shortlisted. If you put AHB, AXI protocol project, and if you put DDR and UART in your resume, it will be easily picked. Why? Because many industries are using these protocols for communication in SOCs, right? So if you put DDR, if you know DDR, easily you can get into any product company. Why? Because DDR is such a good protocol which will be used in RAM communication, right? So DDR4, DDR5 you need to understand. So that we are covering in 5th month. Here you will be doing 2 projects in 4th month. In the 6th month, we will be into scripting. We need also after DDR, we will be covering some introduction to PCIe as well, and then you will be entering into scripting. In scripting, you need to understand Python. Python based scripting or Perl we will be covering, and some TCL scripting. You will be writing some automation codes there. You can't go and read the uh, log always. You can directly write script to understand what is happening after the simulation. That can be automated. So scripting is required here. Then parallelly in preparation, some mock interviews will be conducting you, so that you will be get prepared for the company interview whenever it comes. After 4th month only, here also we will be conducting some mock interview that is not added here. This placement support and interview is what the mock interviews and also the company interviews. But this 3 months program will give you the confidence for design verification role. But industry requires some more advanced features of verification. They will expect from the candidate. So here coverage assertion and these protocols are required. That will be covered in the 6 months course. So these are the protocols we will be covering. Okay, there will be continuous support for the placements. It is not only restricted to the 6 months. And remember, every session recording will be provided, not through the YouTube. We will be putting that in a common SharePoint and share you the link for that. Okay, this is the plan, and you can always contact the mentors, me and any other mentor who is taking you the session. He will be ready to help you, and even after the training, we are there to help you. Okay, if any assistance is required, right? So this is what it is. It is well structured for graduate and also students in final year or in MTech, and also any other candidate who is working in some other domain and want to come to VLSI domain. This is the right place. Okay, and this is our office. You can come down to office if you are in Bangalore. If you want to meet me physically, and you can contact through this number, or you can go through our website once. It will be having all the basic details and also course structure. You can find your see as soon as go there, you will be seeing the pop-up. This is for the 3 to 6 months course registration. Okay, so go through this brochure if you have not gone through once. Okay, so this is all about today's session. And if you have anything to ask me before enrolling to this course, please ask me. Or if you want to get more information about this, you can contact me on the number. Uh, okay, or you can call me or WhatsApp me so that I can respond. Right? Do you have anything in specific you need to, if you want to ask, you can ask. Okay, I will give you the brochure.